going to start out this evening by using yesterday's greeting. May the 4th be with you. These are not the nerds you're looking for. So, welcome to the regular meeting of the Memphis Astronomical Society. Let me get my... And wouldn't you know it, it's sharing the wrong screen. Sorry about that. Okay, there you go. So we are the Memphis Astronomical Society. We've been doing this since 1953 in one form or another. Not as much on Zoom as we do now. And there. And just to prove that we are a real organization, we have our own QR code. So you can snap a picture of that and get to our website and join our email distribution list, or you can join our society as well from that link. So please feel free to do so. And if you aren't super interested in astronomy but support the work we do to try to educate the public and work with younger folk to get them interested in science and education, feel free to join and support our organization. And that QR code takes you to a web page that looks like this, and you've got a couple of options to subscribe to the email list or join our organization altogether. And by the way, it's only $25 a year. That's a good deal at twice the price. Trust me. We have a calendar on our website, and for the month of May, we've got a few events coming up. We've got observing this Saturday night at Hinton Park. This is what we call a telescope mentoring session, where we start before the sun goes down. Get out there early so that we can, see what we're setting up. And if you need help with your telescope, we can help you with it, help you, believe it or not, if you're struggling with your equatorial mount, you are not the first one. I struggled with that for a while. And of course, once you figure it out, it's just like, duh, but it is not intuitive. So if you're having problems with your mount, having problems getting pointed at things, having problems operating your telescope, join us at Hinton Park in Collierville, Saturday night. We also have a public observing session at Bobby Lanier Park in Germantown on Friday, May the 23rd. We'll need volunteer telescope operators to come out and set up for that. Then on the 24th, we have our semi-annual observing at Village Creek State Park. This is the rain date. Our last one was rained out. So that's over near Forest City, Arkansas, and we always can use volunteers for that. So please keep that in mind. And then on Saturday, May 31st, Mylan and I and maybe Jeremy and some others will be out at Beale Street Landing Park downtown, showing downtown outdoor goers the wonders of the late afternoon and evening sky. Mylan does a great job with his solar telescope setups, and then as it gets dark, we try to observe dark sky, limited dark sky things, city lights and everything else. But come on down and join us. There's also a reminder to, if you want to be a part of the President's Volunteers, to help us with our public outreach efforts. I promise I'm going to. It hadn't happened yet. I'm setting up an email distribution list and an ability to communicate with this select group of hardworking individuals that want to help us with our public outreach. And we will continue to review the special privileges and perks for the people that are on that list. If you weren't at the last meeting, you missed picking up your 12 months of the Memphis Astronomical Society sky charts that are all printed on waterproof paper. I have a set of those for everyone that's volunteered so far. And I have, they have one with me. They're all put up. ID badges for everyone, telescope operator, it says. So come see me about your extra special gifts. Since our last board meeting, no, up until our last board meeting. So if I've missed you and you've joined since, my apologies. We'll certainly pick it up next month. Richard Oberg, welcome to the Memphis Astronomical Society. Richard, I know from Jackson, Tennessee. Jason Grosser, Heather Udy, Ilya Green, Scott, well, I'm going to kill that one, Wycliffe, I'm sorry, Scott, David Carroll, and Olivia Denton. So, welcome to the Memphis Astronomical Society. We hope you get out of it more than you expect. We have a newsletter. This month we've got information about our picnic, which we had this last Saturday. Wow, did that turn out great. We've got some information about tonight's presentation, and then some articles about finding exoplanets and how that works. The picnic, by the way, Saturday, you couldn't have asked for better weather. The venue was perfect. It just worked out really well, and fellowship was great. And I want to thank Merrill and Steve and Les for all the work they did, and many others. I don't mean to leave you out if I did, but these were the key folks on the picnic committee, and thank you very much for your hard work and effort to make this the success it was this year. All right, our newsletter has a yet to be used classified ads section. So remember, if you've got a piece of gear you want to sell or something you're looking for, I personally have stuff that if you told me you wanted it, I'd probably sell it to you. So if you've got things you are looking for, let us know. If you've got something to sell, we can get it in the newsletter and perhaps find a home for it locally without having to get on eBay and pay for shipping. The Memphis Astronomical Society has got an astrophotography group with a special focus on astrophotography. And we have a meeting once a month. It's always a Zoom meeting. It's on Wednesday evenings at 7 p.m. And this month we have a few agenda items already outlined, including I will be doing a presentation on how to clean and maintain your telescope optics, both lenses and probably more to the point mirrors. That's the part you've really got to be careful with. So There'll be that and a few other things. So join our astrophotography group and join our meetings on Wednesday, the 21st. Memphis Astronomical Society has bling. We have some cool things that we get our logo put on. If you're not familiar with mass.fits, that's the play on the word misfits, but MAS, of course, Memphis Astronomical Society, and .fits is the file format used for many astrophotography image processing data collection files. So tonight, it's not May the 4th, but Cinco de Mayo. And we have our wonderful guest in the form of Rod Pommier, I think. I hope I said that right, Rod. And his topic is one of my favorites. I absolutely love globular clusters. And so we get to hear more about them, and I'm sure I'm going to learn something. So, Rod, thank you very much for joining us, and I'm going to stop sharing and let you have it.
My name is Rod Pommier. It's a pleasure to be here. You guys really touched my heart when you invited me to speak tonight. And the correct pronunciation of my last name is easy to remember for astronomers because it's Pommier, rhymes with Messier. So astronomers virtually never forget that. So tonight I'm going to talk about glorious globulars. And in my mind, globular clusters are certainly among the most beautiful of deep sky objects. I mean, these dazzling spheres of literally hundreds of thousands, to some cases, millions of stars never fail to delight. And you can almost certainly bet that at any star party or observatory tour, show-stopping globulars like M13 and Omega Centauri will be shown. But sadly, after you get past M13 and Omega Centauri and maybe a very short list of a few others, the trail of globular star clusters in amateur astronomy quickly grows cold. Sadly, if you talk to amateurs, most have viewed only a handful of globular star clusters available in the sky. And given that there are so many that we could observe, I really have to ask, why is it that we don't view more of these? And I think I can explain it, and it comes from a very common, grossly incorrect misconception about globular star clusters. So let me explain that with a story from my life. You see, I used to be one of those observatory tour guides. This is the University of Oregon's Pine Mountain Observatory in the high desert of Central Oregon, where we have really dark skies. And this is the 24-inch dome that houses the 24-inch telescope. And I used to do film astrophotography outside this dome because the University of Oregon would let me run any number of extension cords I needed out the door of that observatory to run my telescope clock drive, my laptop, my dew zapper, a hairdryer, what have you. And they let me sleep in the astronomer's residence during the daytime, where I had a good bed and a refrigerator for food and drink and a stove to cook meals on and even a hot shower. But in exchange for using those amenities, they wanted me to give tours on the weekends to the tourists that showed up and wanted to look through the telescope. So I did that. And so as it got dark, I would gather people inside the dome and give them a talk about astronomy and the telescope and some of the objects that we would view. And on the walls, we had very large posters of images from Mount Wilson Observatory of M13, M51 in Canes Venatici, and M33. And I can tell you that as people stared at those images and saw that enormous telescope hovering above them, their anticipation and excitement about seeing them was palpable. So once it got dark, I would always start the show with M13. Like I said, it's a showstopper, never fails to delight. And the oohs and the ahs and the oh my gods when people would look through the eyepiece for the first time would just reverberate through that dome. And that's because that object through the telescope looked like that picture. In fact, it looked better than the picture, because if you look at this picture, the central core of this is just burned out white blob. But when you look through the eyepiece, you could see stars resolved all the way down to the core. That was not the case with the other objects I showed that night. When you looked at M51, well, first of all, it's really tiny. I mean, any of us who've ever observed it or tried to photograph it know it's nowhere near as big as we're led to believe in these images. And so all people could really see of the whirlpool was this bright central core of M51, the core of NGC 5195, the companion galaxy, and this brighter spiral arm coming out of the core. But nobody ever saw the spiral arm connecting the two. It is just too faint. So people would look through the eyepiece and just say, that's it. And I'd say, yep, that's it. It was even worse with M33. It's so big and so diffuse and so faint. They would look through the eyepiece and say, where is it? I don't see anything. And I said, well, it's actually filling the whole eyepiece. And they'd look again and say, oh, is it that little fuzzy thing in the center? And I'd say, no, that's just the bright core of the galaxy. Now, if you use that averted vision trick I talked about, you'll see an oval around that that's just barely brighter than the background sky, and you might see an S-shaped thing snaking through it. And so, suffice it to say that the disappointment that people had when I showed them other deep sky objects knew no bounds. So I'd quickly revert back to globular clusters to avoid having a riot on my hands. And there were plenty of them. I could go to M3 and Canis Venatici, drop down to M5 and Serpens Caput, over to M10 and 12 and Ophiuchus, down to M4 and Scorpius, over to M22 and Sagittarius, M22 and Sagittarius, M2 and Aquarius, and oh look, M15 is even rising in Pegasus to give us yet another. And there was a problem, because there was always a group of jaded, and I mean jaded, amateur astronomers who were in the group. And I get it. They drove hours to get to the high desert of Central Oregon because they wanted to see the faint fuzzies through the 24-inch telescope and perhaps get better views than they get through their own telescopes back in light-polluted cities. So it wasn't very long before one of them would literally yell at me and say, stop showing us globular star clusters. And then came the words that just wounded my heart. If you've seen one globular cluster, you've seen them all. Well, I'm here tonight to tell you that is simply not true. While I will admit that globular star clusters may not exhibit the infinite variations of size, shape, and arrangements that we find among other classes of deep sky objects, they still exhibit considerable diversity if you know what to look for while observing. For example, did you even know that there are 12 different classes of globular star clusters? Well, there are, and we'll go over those a little bit later on. But think about it. If you just set out on a task to observe maybe half of these classes as an example, it would keep you busy for quite a while and increase your repertoire of globular clusters quite a bit. So here's a program outline for tonight. We're first going to learn as much as we can about globular star clusters, what they are, how they form, and some of their tremendous significant contributions to cosmology and astronomy, and even some things that you might not know about, like their presence in science fiction literature and the search for extraterrestrial intelligence. And then we're going to learn about what makes globular clusters distinct from one another, so that when you view them, you don't really view them as being all the same. And then at the end, we'll be having some questions and discussion. So let's get excited about globular star clusters. So why observe globulars? Well, as I already said, they're beautiful. But let's not forget they're colorful. They have red giants and blue stragglers. And if you have a big enough aperture, you can actually see some of these colors. And that's a frequent thing at big star parties where people have 30-inch dobs and things like that. And that's enough aperture to bring some of that color out. They have very large apparent sizes. A lot of globular star clusters are a substantial, and I repeat, substantial fraction of the size of a full moon. And that means you can observe them with various systems. So if you have a short focal length system, you get to appreciate a globular in the context of its surroundings in the sky. On the other hand, if you have a long focal length system, you can zoom right in for high resolution in the cluster itself. They're bright, and that means they're easy to find in your finder scope, and you can observe them while the moon is brightening in the sky, where you can't pick up faint fuzzy galaxies and nebulae. And that also means you can observe them from light polluted cities, which is where a lot of us live. And you don't need expensive narrowband filters to enhance the view, with perhaps one exception that I'll talk about later on. So what are globular star clusters? Well, they're spherical conglomerations of many, as I said, typically hundreds of thousands to, in some cases, millions of stars that are very tightly bound by gravity, which makes them incredibly stable. It's actually would be very difficult to gravitationally disrupt a globular star cluster. They all orbit the Milky Way within a spherical halo that surrounds the plane of its disk. And that means that typically these things are going to lie at distances of tens of thousands of light years from Earth. It's a characteristic of globular star clusters that the stars are generally concentrated toward the center of the cluster. And that is the basis of the classification system that we're going to be talking about a little later on. But what it really means is that these things have incredible densities of stars in their core regions. For example, if you took a 10 cubic light year volume around the sun and you situated it just right with the sun at one corner, you could get about 5 stars in that cube, which would be the sun, 3 stars in Alpha Centauri, and Sirius. The same volume in a globular star cluster will typically contain 400 stars, and in the cores of some of the denser clusters, 1,000 stars. Another way to look at this is photometrically. So this is M2 in Aquarius. It's one of the largest and densest globular star clusters known. And it turns out that a 1 by 1 arc-minute area in the center of this globular star cluster puts out a whopping 37% of its total light volume. An equal area, just a few arc minutes off the center, turns out puts out a mere 0.02% of its light output. So that tells you how incredibly densely packed this globular star cluster is. Within the core, stars are only light days, not light years apart. And that means if you lived on a planet orbiting a star in a globular cluster, your skies would be perpetually bright. How bright? Well, about as bright as 20 full moons in our sky. So this is actually the topic of a very famous science fiction novel written by Isaac Asimov in 1947 called Nightfall. And in this novel, I mean, science fiction critics say this is one of the best science fiction stories ever written. Currently, science fiction stories win an award called the Nebula Award, which I think we could all relate to as a good title. The nebula didn't exist in 1947, but people all agree if it had existed in 1947, this would have won the Nebula Award. So in this story, there's a civilization on a planet that orbits 6 suns, at least one of which is always up on every single part of the planet, which means the people that live there have absolutely no concept of nighttime or dark. The only time they experience dark is if they go in a cave or a room with no windows in it, and they're actually a little afraid of the dark. And because their skies are constantly bright with these 6 suns, that's all they see in the sky. And so they believe that their system is all there is to the universe and that they are alone in the universe. Now, they do have solar astronomers who are tracking the movements of their suns. And by tidal effects, they figure out there's a dark moon in the system that they didn't know about. And it's going to eclipse one of the suns when it's the only sun in the sky and part of the planet. And that eclipse occurs once every 2,049 years. So they all go to that part of the planet because the eclipse is coming up. And when it occurs, 30,000 bright stars appear in the sky. And of course, the implication of that is that this civilization lives within a globular star cluster. So I'm not going to give you any spoilers and tell you what happens when these people find out their belief system is completely wrong and they're not the only star system in the universe. But if you haven't read this, really go read it. It's a great story about a globular star cluster civilization. So how many globular clusters are there? Well, we believe that all major galaxies do have globular star clusters. And we now have very good proof of this, that they have been there from the very beginning of galaxy formation based on new images from the James Webb Space Telescope. So here is an image on the left of some of the most distant primitive galaxies that the James Webb has yet imaged. And on the right, we've got 3 vignettes from the little elliptical galaxy up at the top, an edge of a spiral galaxy here in image number 2, and then another elliptical down at the bottom is image 3. But if you look at these, you can see that they are dotted with these little golden blobs orbiting in halos, and those are globular star clusters. So we know that globular star clusters are there from the very, very earliest time of galaxy formation. The Milky Way has 157 known globular star clusters. Now, we believe there are many more, but we just can't see them because the vastness of the Milky Way blocks our view of them. Now, notably, 29 of these 157 are Messier objects. And while they're distributed from M2 in Aquarius all the way up to M107, notably, 12 of the first 24 objects in the catalog, a full 50%, are globular star clusters. Now, there are globular star clusters in other Messier galaxies. For example, the Pinwheel galaxy M33 in Triangulum has 122 known globular star clusters. And if you're an astro imager like me and you've taken an image of M33, you may have captured some of them without even knowing it. I have. Here's an image of M33 I got published in the November 2014 issue of Astronomy, and it turns out I captured 11 of M33's globular star clusters in this image. I probably captured many more, but I have not found any way that I can identify them. M31, the Andromeda galaxy, has 400 globular star clusters. And again, if you've imaged M31, you have probably captured globular star clusters in those images. This is an image I got published in Astronomy magazine in the December 2017 issue, and the actual subject of the photograph was the giant star cluster NGC 206, which is one of the largest star clusters known. It spans 4,000 light years from end to end. But it turns out that I also captured 18 of M33's globular star clusters in this image, which is more than half of what we have in our Messier catalog. Here's another image I got published in Astronomy magazine. This went with an article I wrote about using Hubble's Cepheid variable, M31V1, which I've got marked in tick marks, just like Hubble did on his original plate. And I used that to reproduce Hubble's measurements and measure the distance to the Andromeda galaxy. But it also turns out that I captured 35 of M31's globular star clusters in this image, which is more than we have in our own Messier catalog. Other galaxies in the Messier catalog have thousands of globular star clusters. So this is M104, the Sombrero galaxy in Virgo, which lies at a distance of 29 million light years, and it is known to have 2,000 globulars. And if you look at this image, you can sort of see some little dots hovering around in a halo around the disk of M104. And if you zoom in here, you can actually see a couple dozen globular star clusters that I captured at a distance of 29 million light years. The record holder for globular star clusters in a galaxy is M87 in Virgo, which lies at a distance of 53 million light years. And you can see in this image I shot a number M87 with some of its, surrounding galaxies. But if we zoom in on this, it's known to have 15,000 globular star clusters. And in this zoom, besides seeing the relativistic blue jet being shot out of the supermassive black hole at the core of this galaxy, I've counted over 150 globular star clusters that I captured around M87 just in this area. So turns out you can photograph globular star clusters at distances of 53 million light years from here. But I think a real reason to want to observe globular star clusters is because of their tremendous cosmological significance to astronomy. For example, they were key in determining our location within the universe. So this is Harlow Shapley. He was the director of the Mount Wilson Observatory in the early years of the 20th century. And he used the 60-inch reflector atop Mount Wilson, built by George Ellery Hale, to measure the distances to as many globular star clusters around the Milky Way as he could. And what he found was that they occupied a spherical distribution around the plane of the Milky Way galaxy. And he found that in the direction of the summer Milky Way, there were globular clusters at close distances, moderate distances, and even extremely far away distances. When he looked in the opposite direction toward the winter Milky Way, he only found 3, including this one, which is M79 in Lepus. This is one of the very rare wintertime globular star clusters. But this one's always held a special place in my heart, not just because it allows me to watch a globular in the wintertime, but because of the tremendous role it played in determining our position in the universe. So what Shapley did is he correctly assumed that this spherical volume of globular star clusters had its center coincident with the center of the Milky Way. And with that assumption, the only way he could explain that there were globular star clusters at close, moderate, and extreme distances in one direction, and only a few nearby ones in the opposite direction, is if we were not at the center of the galaxy, but about halfway from the center out toward the edge of the disk. And this gave us our biggest demotion of position in the universe since Copernicus put the sun at the center of the solar system. Globular star clusters have also played a key role in determining the age of the universe. So how do you determine the age of a star cluster? Well, you do it by plotting what's known as a Hertzsprung-Russell diagram. So on this graph, along the x-axis, we have classes of stars going from blue supergiants down to red dwarfs, which is also a reflection of their temperature, being the very hot stars on the left and the cooler stars on the right. And on the y-axis, you plot their absolute magnitude. And you assume that all of these stars were born at roughly the same time out of the same nebular cloud, but they form stars of various sizes depending on the size of those globules of hydrogen. And if you plot that, then you'll find that the majority of the stars fall on this squiggly line from the upper left to the lower right, known as the main sequence. This is where stars, regardless of their size, will plot when they are fusing hydrogen and hydrogen into helium, which is what they do for most of their lifespan. And eventually, all stars will use up all their hydrogen and they run out of fuel. So they begin collapsing under their own weight until the pressure in the core gets high enough to fuse hydrogen or helium and helium into carbon. And that produces a lot more energy than hydrogen fusion. So the star expands greatly and cools as it does and becomes a red giant. So they shift directly to the right of the stars that gave rise to them. And it produces this horizontal branch like you see here. This is where the red giants plot. So the rest is just physics. If you go to blue supergiant stars, they live fast and die young. They use up all their hydrogen within just a few million years and convert to red giants. So if you see the horizontal branch coming off up here at the top of the graph, that star cluster is only a few million years old. If you go down to a class A star like Vega, they're smaller, so their hydrogen lasts longer, about 1 billion years. So if you see the horizontal branch coming off here, then that cluster is about 1 billion years old. We know the sun is a class G star, and we've calculated it has enough hydrogen to last about 9 billion years. So if you saw a horizontal branch coming off to the right of class G stars, that star cluster is about 9 billion years. Well, we've plotted Hertzsprung-Russell diagrams on globular star clusters, and they do have a horizontal branch, and it's quite short, and it's way down here, which tells us that the age of globular star clusters is about 12 to 13 billion years old. So this means that globular star clusters are actually the oldest thing that you can see in the sky. Now, this created a tremendous paradox when Hubble found out that the universe was expanding. So this is a very famous graph from his study of the relationship between the redshift of a galaxy and its distance. So along the x-axis here, we've got the distances out to galaxies that he calculated using various means. And on the y-axis, he plotted their recessional velocity based on their redshift. And he got this very nice linear correlation. It's a straight line going up at essentially a 45-degree angle. So what he found was that a galaxy that was twice as far away as another was receding twice as fast, and one 4 times farther was receding at 4 times its speed. And so the slope of this line is known as the Hubble constant. And it was originally, after some corrections, found to be a speed of 250 kilometers per second per megaparsec of distance. Now, the fun thing you can do with this is you can take that speed and run it backwards in time and figure out by exponential mathematics when were all the galaxies together in a clump, which would have been the origin of the universe or the Big Bang. And using this speed for the Hubble constant, they came up with an age of only 4 billion years. So you can see the tremendous paradox that created. How can you have globular clusters at an age of 12 to 13 billion years old when apparently the universe is only 4 billion years old? So astronomers came up with very clever ways to try to explain away this paradox between the age of globular clusters and the Hubble constant. So this is a graph from one of my favorite old astronomy papers, and you can tell it's old because the ink from the other page gets stuck on the graph here. But what they plot here is the age of the universe along the x-axis and its size on the y-axis. So at time 0, we had a Big Bang and the universe began expanding, but it slowed down due to its own gravity. And so at an age of 4 billion years, you would get a Hubble constant that matches that of 250 kilometers per second. But then they proposed that the universe just kept slowing down and barely expanding, and goes into what they called a prolonged loitering phase where it barely expanded at all. And then they got really creative. They posited that maybe there's some as yet undiscovered force in the universe that starts the universe expanding again and running away towards a runaway expansion. This was almost prescient to the concept of dark energy, which hadn't been discovered yet. So if that happened, I lost part of my graph. I don't know how to explain that. Then there we go. Then there would be another time where the Hubble constant would have read for us the same slope of 250 kilometers per second, which would make the universe look like it was 4 billion years old. And they could basically arbitrarily say this prolonged loitering phase was as long as they wanted. So they said, what if you say it's 13 billion years, and that's now, and now we have a Hubble constant of 250 kilometers per second, but we can have a universe old enough to hold 13 billion-year-old globular star clusters. So that was all very creative, but it all turned out to be wrong because Hubble's estimate of the Hubble constant was wrong. So we've since come up with a much better standard candle to measure the distances to galaxies, and those are type 1a supernovae. And we can track those out to tremendous distances in megaparsecs. And of course, we can still get their redshift. So this gives us a much better relationship of the Hubble constant. And it turns out that all of Hubble's data on that first graph I showed you fit in that little red box down in the corner. So you can see how a little variation up or down would have given you a wrong reading. So using these modern data, we now get a Hubble constant that's much lower of only 73 kilometers per second per megaparsec, which means that the age of the universe, if you run the clock backwards, is 13.4 billion years. So we now have a universe old enough to harbor 13 billion-year-old globular star clusters. Of course, there's another way to measure the age of the universe, and that's with the cosmic microwave background radiation. And when we do that, we get a Hubble constant that's still a little bit lower of 67 kilometers per second per megaparsec. And if you run the clock backwards on that, you get an age of the universe of 13.7 billion years. So this is now known as the Hubble tension. Which constant is correct? Is it 73 kilometers per second based on type 1a supernovas, or is it 67 kilometers per second based on the cosmic background radiation? And astronomers are really hoping that this will meet somewhere in the middle and we'll actually finally get it right. You may not know it, but globular clusters have made a very important contribution to the search for extraterrestrial intelligence. So this is Frank Drake. He was a famous astronomer who died a little over 2 years ago. And he was the founder of the search for extraterrestrial intelligence. He started doing this at Green Bay, West Virginia, at the National Radio Astronomy Observatory, where he started the Ozma project. Ozma was the princess in the Wizard of Oz stories by Frank Baum. And what he did is he listened to nearby stars like SETI and Epsilon Eridani for radio broadcasts from a potential intelligent civilization. But Frank Drake is much more famous for publishing the Drake equation in 1962. So the Drake equation is an estimate of the number of intelligent civilizations in our galaxy, which is the number n. And it's a string of variables. And so it's R star, which is the rate of star formation in the galaxy, times FP, which is the fraction of stars that have planets, times NE, which is the number of planets per star that are in the Goldilocks zone where you can have liquid water, times FL, which is the fraction of those planets that develop life, times FI, which is the fraction of those planets that develop intelligent life, times FC, which is the fraction of those civilization or intelligent life that go on to have a civilization, times L, which is the length of time that civilization exists before it gets wiped out by cosmological forces or destroys itself. Now, this equation, as clever as it is, can be manipulated in different ways. Some astronomers throw in very liberal values for all of these variables, and they come up with thousands or hundreds of thousands or millions or trillions of intelligent civilizations in our galaxy alone. On the other side of the coin, astronomers can throw in incredibly conservative values and make n come out to be 1, which is us. So we really don't know very many of these things. We know the rate of star formation. The Kepler Space Telescope has helped because it's giving us some clues as to what fraction of stars have planets and how many of those planets might be in the Goldilocks zone. And later on, I'll show you Frank Drake's own estimate of the value of L. But Frank Drake is much more famous for the Arecibo message. This was a message sent from the Arecibo radio telescope in Puerto Rico. And here's that telescope, which recently collapsed, sadly. But the first thing Frank Drake did when he got there was calculate that if this was a cereal bowl, it would hold 350 million boxes of cornflakes. But the amazing event occurred on November 16, 1974. So it recently had its 50th anniversary. And on that day, he broadcast a message into space with an energy of 30 trillion watts, which made Earth the brightest radio source in the universe for about 3 minutes. So this message was binary. It was 1,817 bits broadcast at a speed of about 10 bits per second. And he made it binary by broadcasting 2 different frequencies. The carrier frequency was 2,380 megahertz, which if you want to think in binary, you can think of being a 0. And at various times, he modulated it up to 2,390 megahertz, which if you think in binary could represent a 1. Now, this is a brilliant exercise in how could you possibly communicate with an alien civilization if the only 2 things you developed in common were mathematics and a knowledge of chemistry. So 1,817 is what you call a super prime number because it's the product of 2 other prime numbers, namely 23 and 79. So we'd assume that they would figure that out. And so if you imagined the 0 to be a dark pixel and the 1 to be a bright pixel, and you arrange this signal in a grid of 23 by 79, you would get this message. It wouldn't be color coded. This is done to just describe different aspects of it. So all throughout this message, he put lines at the bottom of things, and this is just to tell you where to begin reading, because they wouldn't necessarily be reading from top to bottom or left to right or right to left. So it tells you how to read the message. You always start from this line. So at the top is mathematics. He counts 1 to 10 in binary. Then reading from here, there are a series of numbers, 1, 6, 8, 9, and 15, which are the atomic numbers for hydrogen, carbon, oxygen, nitrogen, and phosphorus, which are the basis of life on this planet. And then this is a basic sequence that tells you what to expect, which numbers to expect in these positions. So this is the formula for the chemicals of DNA. This is deoxyribose and phosphorus on this side, which makes up the 2 chains of the double helix. And it tells you that this is carbon for oxygen 5, or hydrogen for oxygen, it's hydrogen 5, carbon 4, got to read binary, nothing in that one nitrogen, and no phosphorus. And this is the formulas, then empiric formulas for adenine, thymine, cytosine, and guanine, the 4 base pairs in DNA. And down here, he drew a picture of the double helix of DNA. And this is 5 billion in binary, which is the number of base pairs we thought was in the human genome. Then there's a stick figure representing what we humans look like. And this is a blue bar representing a span. And this is the number read sideways of 14 to tell us how big we are. So, and down here, we have the number of humans on the planet at the time the message was sent, which was 5 billion. So this is another 5 billion in binary. This is a model of our solar system showing the big sun, small planets, big supergiant planets, and giant planets, and even Pluto was still considered a planet. And he knocked Earth out of the sequence to tell you where this message came from. And here was a picture of the Arecibo radio telescope that sent it, again, with an indication of how big it is. Now, you got to wonder, how would you agree on size if you're telling people how big humans in this dish are? Well, it's the wavelength of the radio frequency. And so it's like we are 14 wavelengths of the radio frequency, and this is about 1,000 feet in diameter for that. So he got to send this message once for the cost and the energy that it took. So the question is, where would you send it? So he chose to send it to globular cluster M13 in Hercules because it contains about 1 million stars, and God only knows how many planets around it, the stars. So it's the best way to get potentially many, many civilizations in a single broadcast. So it will take 25,000 years for that radio signal to reach M13. If anybody responds, it'll be 25,000 more years before we get the answer. So I have a few Frank Drake artifacts in my astronomy collection. This is actually one of Frank Drake's wine glasses. And you can see he has his Drake equation painted on the glass. I have Frank Drake's lecture notebook from his college course he taught on life in the universe. And here you can see his own estimates of the value of L. And he put down all kinds of ways that a civilization might come to destruction, like cosmic accident. But he basically says that he thinks the value of L, that an intelligent civilization that would receive this signal would almost certainly be immortal. One that would last almost forever because they somehow achieve immortality, and that their average span has to be on the order of about 10 million years, which I thought was very interesting. And here are his calculations as to how far away you could detect a signal from Arecibo if you yourself had an Arecibo-sized dish. And he says that with an energy of only 3 megawatts, you could reach the far edge of the galaxy. And as I told you, he broadcast this with an energy of trillions of watts. So that message is going to go way out into intergalactic space. All right, so let's get back to observing globular star clusters now that we've got a lot of reasons to be interested in them. So what makes viewing one globular star cluster distinct from viewing another? Well, there are several things that do that. One is their Shapley-Sawyer class. Then we have features that we can actually see within a globular star cluster. There are foreground objects that go with a globular cluster, and likewise, there are background objects behind globular clusters. And then we can always bring up interesting facts about various globular star clusters. So let's go through these one at a time, beginning with the Shapley-Sawyer class. So once again, this is Harlow Shapley, and while he was working on globular clusters, he teamed up with Helen Sawyer, who was an astronomer at the Mount Wilson Observatory, later became Helen Sawyer Hogg when she married another astronomer in 1930. And together they formulated the Shapley-Sawyer classification scheme for globular star clusters. Now, Helen Sawyer Hogg is one of my favorite astronomers, and this is a book she wrote and published in 1976 called The Stars Belong to Everyone. So if you have a friend or a relative you're trying to get interested in astronomy but doesn't want to make the plunge to getting a telescope, this book is 100% visual astronomy, and it's absolutely captivating and fascinating. So it will hook them and get them into getting their own telescope very soon. So the Shapley-Sawyer classification system divides all globulars into 12 different Roman numeral classes, 1 through 12. And they developed this system between 1927 and 1929. Now, I wrote an article in the August 2014 issue of Astronomy that goes through this classification system in great detail, so you're welcome to find that and read it. But I'm going to give you the Reader's Digest version here to make it quick. So when we look at classes 1 through 4, what they all have in common is that they have dense, essentially unresolvable cores. And with class 1, most of the globular is this dense, unresolvable core. And as you move up towards class 4, very little of it remains as a dense, unresolvable core. With classes 5 through 8, the cores now become resolvable, and this gives you the snowball of stars effect that we see typically with M13 and Omega Centauri. But as you get higher and higher from 5 to 8, you see these stars spread out more and more and more. And then you get into the higher classes, 9 through 12, the cores actually break apart, and you can see gaps between the stars in a globular star cluster. And as you get up towards class 12, the gaps become so wide and so numerous that it basically becomes indistinguishable from a circular open star cluster. And it gives you the impression that if you had an infinite amount of time, you would actually individually count every single star in the globular cluster because of the gaps. Also, as we move from class 1 to 12, there's a general increase in what I call the beehive effect, and that's the number of scattered stars out peripheral from the globular star cluster. So if we look at the Messier catalog, we have an example of each one of these classes except for class 12. Turns out that class 5 is the most frequent in the Messier catalog. There are 7 globulars in the Messier catalog with class 5. These are what are considered to be the archetypal examples of each of the 11 classes that are in the Messier catalog. And I'm not going to go through each of these and show you an example because virtually every one of these globular clusters I have listed as an archetype, I'm going to show later on as an example of something else. But from now on, when I show a globular cluster, I'll put its Shapley-Sawyer class below its title so you can see what that class is and start to get a concept of this. So let's move on to something that's a little more interesting, which is features within globular star clusters. And there's one that's really famous, and these are the dark lanes in M13 in Hercules. So this is a drawing made by Irish astronomer Bindon Stoney in about 1850 when he was looking through William Parsons, the 3rd Earl of Ross, 72-inch Leviathan telescope at Burghcastle in Ireland. And what he saw and drew was this Y-shaped dark figure in the middle of the core of M13. And you can see that he drew that there are some stars in front of this that are members of the globular cluster. So the modern name for this structure is the propeller because it resembles 3 blades on a propeller of an airplane. So this is my image of M13 in Hercules. It's a class 5 globular, so we're into the snowball of stars effect. And after I shot this, I sent it in to Michael Bakich, the photo editor at Astronomy, and I wrote to him and I said, Michael, I know my chances of getting an image of M13 published in the magazine are equivalent to those of a snowball in hell, because everybody sends you their picture of M13. But I think this shows the propeller really nicely, so I thought I'd send it to you anyway. And it quickly wrote back and said, Rod, you're absolutely right. Your chances of getting a picture of M13 published in this magazine are equivalent to those of a snowball in hell. He said, but I just pulled a whole bunch of images of M13 submitted over the past 15 years or so, many by astrophotographers I'm sure you know. And he said, you're also right. He said, those images don't show the propeller quite as well as yours does. So you beat the odds and I'm going to publish it. So this got published with the propeller in the 2018 issue of Astronomy. And then Stephen James O'Meara, he writes a monthly column in Astronomy about a various topic. And in the October 2019 issue, he wrote an article on the propeller. So they used this image a second time, again, because it shows the propeller so well. Now, what the propeller is hotly debated. Some astronomers think that this is merely gaps between stars in the globular star cluster, and others think it's dark material inside the globular cluster that's occulting other stars. It is not anything between us and the globular star cluster, because again, you can see globular stars between us and it, and these were even drawn by Bindon Stoney. Nonetheless, the fact that there is dark obscuring nebulosity in a lot of globular star clusters has been known for decades. These are two of the classic papers from the early 1960s that describe this phenomenon. And we can see this dark obscuring material in a lot of globular clusters when we observe them, if we choose to look for them. So this is going back to M2 in Aquarius. It's a class 2 globular cluster. Remember, I said it was one of the densest globulars known. But if you look down at the bottom here in the periphery, you can see this dark lane cutting across it. And this image got published in August 2024 issue. But this is a book by John Hallis and Everett Krimer called the Messier Album. And in this book, they cover all 110 Messier objects. And Everett Krimer photographed each of them through a 12.5-inch cave reflector. And John Mallis drew chalk pictures of all of them as he saw them through a mere 4-inch unitron refractor. So if you go to the page for M2, you can see the photograph by Krimer and Mallis's picture down at the lower right. And you can see he drew that dark obscuring lane cutting through that and putting a few stars in front of it. So these are things that are definitely observable. This is M92 in Hercules, and I say too bad, because everybody looks at M13 in Hercules, and that has the bad effect that everybody ignores M92 in Hercules, which is a nearly equal beautiful star cluster. But if you look over to the right here, there is a dark globule that you can visually spot on the very edge of M92. And if you zoom in on that, I thought that looked like a question mark without a period. So I dubbed this thing the question mark nebula in M92. And this got published in the 2019 March issue of Astronomy magazine. This is M3 in Canis Venatici. It's probably the second most famous northern globular star cluster after M13. And I think what's really interesting about this globular cluster is that if you look carefully, you can actually see a line going nearly entirely across the globular cluster, almost like a crack in an egg. And so if you zoom in on that, there's that. It's this incredibly long string of dark material blocking out stars behind it. And this is a visual feature that you can spot. Perhaps the dirtiest star cluster in the Messier catalog is M12 in Ophiuchus. It's a class 9 globular star cluster, and it's just riddled with dark material blocking out views of the stars in multiple areas behind it. So when you look at this globular cluster through a decent sized telescope, it looks like it's been slashed by a knife or a box cutter, because it's got so many cuts and stripes through it. Moving on to other types of objects we can see in globular star clusters. This is M13 in Pegasus. It's a class 4 globular star cluster, so it's just holding on to a shred of unresolvable core at the center. And while we can see a lot of blue stragglers in this cluster, I got this published in July 2020 issue of Astronomy because of that. That is not a blue straggler. That is the planetary nebula Peas 1. And so this is the one case in which you use a narrowband filter. This is oxygen 3 data that I shot through an oxygen 3 filter and then I mapped it to the teal color of a planetary nebula and then added it into the rest of the image. So you can also see this with a hydrogen alpha filter or photograph it with a hydrogen alpha filter, in which case you would map it to a more red color. So this is actually a planetary nebula in the globular cluster. And we know it's in the globular, not in front of it, because the Doppler shift of the emission lines of this planetary nebula precisely match the Doppler shift of the stars in the globular cluster. So let's move on to foreground objects. Most of the time when we're looking at globular clusters, they're far away from the plane of the Milky Way because that's where they see them. And that means, like here with M5 and Serpens Caput, which is a class 5 globular, the rest of the sky is pretty much devoid of stars. But this is M56 in Lyra. And I also say too bad because everybody looks at M57, the tiny ring nebula in Lyra, and few people shift their telescope a short distance towards Albireo to gaze upon this gem. This is one of the smallest globulars in the Messier catalog. It's class 10, so it's the stars, when you look at it visually, are really breaking up with lots of visual gaps between them. It's one of the smallest, literally physically, because this lies at a distance of 30,000 light years, but it's still smaller than virtually all the other globulars in the Messier catalog. But to gaze upon this globular cluster amidst a field of beautiful, colorful Milky Way stars is really a treat. And so this was published in the August 2024 issue of Astronomy. This is M22 in Sagittarius. It's a class 7 globular star cluster, and it's in the middle of the Sagittarius Milky Way. So again, surrounded by countless Milky Way stars. And this globular star cluster, if you photograph it, it's actually not a white globular cluster, it looks yellow. And that's because there's so much scattering by intervening galactic dust. And the blue stragglers in this cluster turn out quite a bit paler than the blue foreground Milky Way stars. And one thing that always grabs my attention when I look at M22 is this line, very straight line of stars, starting with foreground Milky Way stars, but leading into visual stars you can see in the cluster. And then again, if you look at the bottom periphery of this cluster, you can see all kinds of squiggly dark things going back to that dark nebulosity I talked about that go all the way across the bottom of this globular star cluster. But when it comes to a globular cluster in a star field of the Milky Way, M71 in Sagittarius takes the Oscar. This is a class 11 globular star cluster, so we now have very prominent gaps between all the stars. And for 2 centuries, people thought that M71, because it was in the middle of the Milky Way like this, was just another open star cluster and not a globular. But in the latter part of the 20th century, people plotted a Hertzsprung-Russell diagram on it and found it does have that short horizontal branch down at the bottom, giving incontrovertible proof that this is truly a globular star cluster. And here's M79. The thing I like about M79 again is that we have this nice little arc of red giants going in a semicircle, comes to a sharp point, and then trailing stars going off to that. So you can find countless, variations of stars in the foreground of these things. So let's move on to background objects. So this is going back to M13 and Hercules, and when I showed this picture, perhaps the hawk-eyed among you noticed this galaxy in the background. This is IC 4617. It's a spiral galaxy that lies at a distance of 550 million light years. So here we have M13 in the foreground at a distance of 25,000 light years. This galaxy in the background at 550 million light years. So an incredible depth of field. I don't have a lot of field of view with my telescope, but many of you will know that up to in this direction is the galaxy NGC 6207. It's a much larger spiral galaxy. It lies at only about 30 million light years, but again, gives the viewer a real sense of field of view depth. Going back to M92 and Hercules, again, the hawk-eyed among you may have spotted this galaxy in the image, and that's MCG7 3558, and it lies at a distance of about 500 million light years, again, giving us an incredible depth of field. So a lot of the globular clusters, being that they are frequently found way away from the plane of the Milky Way, that's going to be where you have rich backgrounds with lots of little background spiral galaxies that you can look for and spot when you're viewing globular star clusters. And so lastly, we'll move on to interesting facts about globular star clusters. So this is a map of the Milky Way, and the arrow shows our location. So most of the time when we're viewing deep sky objects other than galaxies, we're looking at objects that are very close to us in the Milky Way. And these are very beautiful, diverse objects. And surely the rest of the Milky Way must be harboring countless other beautiful things that would just be wonderful to look at. So do you ever wonder, like me, if you could see something off in the delta quadrant of our galaxy that isn't visible from here? Well, there's one way you can, and that is with the globular cluster M75 in Sagittarius. This is the only class 1 globular in the Messier catalog, and it is lying at a tremendous distance of 63,000 light years from Earth. And the reason we can see it is because it's a class 1 globular. It's so densely packed that it will shine brightly from that distance. So what is happening when you are viewing M75 is that we're located here, and you're peering past the southern side of the core of the Milky Way galaxy and picking up this globular cluster, which is hovering over the outskirts of the far side of our galaxy. And so this was published in the August 2024 issue of Astronomy magazine. And this takes us into a very new, interesting field of galactic archaeology. So this is the Gaia Space Telescope, which was launched by the European Space Agency in 2013. And its job was astrometry. It was to map the locations and speeds and distances of 2 billion stars in the Milky Way, which is a mere 1%. So it got the distances to all these stars from parallax. It would measure the apparent position of a star 6 months apart when we are on opposite sides of the solar system. And then it rephotographed all of those stars from the same position in its orbit 5 years apart, so that we could pick up the actual proper movement of that star and see how much it had actually moved on its own. It holds 2 spectrographs. One is a chemical spectrograph that picks up spectral emission lines so that we can detect the elemental composition of the star and what abundances those elements have within various stars. And the other one is a Doppler shift spectrum. So it picks up the spectral lines and whether or not they're blue shifted or red shifted, and by how much, so that we can calculate the actual velocity of that star towards us or away from us. And if you have the proper motion and the Doppler shift, you can get that star's full dimension 3D vector in space. Now, what this did is it identified a lot of families of stars because they had essentially identical chemical fingerprints, meaning they were born out of the same nebular material. And a lot of those families of stars are found in star streams, little rivers of stars flowing through and around and over and below the Milky Way. So what they did is they took all of these data. They took the chemical signatures of the stars, their 3-dimensional velocity vectors, From the spectra, they can also figure out how big the star is and calculate its gravity. And they put it into a supercomputer with a neural network. And then they ran the clock backwards to figure out how our galaxy formed over the past billion years. And so this generated a lot of papers in the 2020 issues of the monthly notices of the Royal Astronomical Society. So I was recently elected a member of the Royal Astronomical Society. So a cool thing, I'm a fellow. So the cool thing I got to do was go there and do this research in their library. And they have a lot of historical holdings there. And this picture is of Francis Bailey. He of Bailey's beads of solar eclipses. And I'm happy to report that on the mantelpiece below that fireplace, they have images of Bailey's beads. And those are my images of Bailey's beads from the 2017 and 2024 Great American Solar Eclipses. So what this found from the e-mosaics, that stands for modular, well, never mind. They found that our galaxy was formed out of collisions with several other galaxies. So the first collision was with a galaxy that's been dubbed Kraken. That collision occurred 11 billion years ago when this small elliptical galaxy collided with a formless, diskless, barely rotating elliptical Milky Way. And that increased the volume of our Milky Way galaxy by about 10%. The next major merger occurred 9 billion years ago when we collided with another elliptical galaxy that has been dubbed Gaia Enceladus. And it added another 10% of the stars and gave rise to the Milky Way's disk. Virtually all the stars in the Milky Way's disk can be attributed to either adopted stars from Gaia Enceladus or stars formed out of a mixture of Gaia Enceladus hydrogen with Milky Way hydrogen. And then the last merger I'm going to talk about is that with the Sagittarius dwarf elliptical galaxy. That is a collision that began 7 billion years ago, but this merger is not yet complete. So it turns out that the Gaia Enceladus merger completely changed our concept of where globular star clusters come from. Historically, we thought that all of the Milky Way's globular clusters were believed to have formed from leftover gas in the nascent Milky Way's outer halo. But when they ran the e-mosaic simulations backwards, they found that when we collided with Gaia Enceladus, it brought a lot of its globular clusters with it, and they have since joined our Milky Way. They survived the merger and now orbit our Milky Way galaxy. And these include M2 in Aquarius, M56 in Lyra, M79 in Lepus, and M75 in Sagittarius. So some of the interesting things you can talk about, besides the fact that these are not original Milky Way globulars, they came from another galaxy, is that it turns out M75, unlike all the other globulars in the Messier catalog, it orbits us in a very highly elliptical orbit, which is a clear proof of its extragalactic origin. Even stranger's M56, it's the one globular in a system that is in a retrograde orbit around the Milky Way, going around us in a completely opposite direction from all of the other globular star clusters and even the direction of the Milky Way's rotation itself, which again is very strong proof of its extragalactic origin. Much of the Milky Way's current morphology as a barred spiral elliptical galaxy is directly attributable to our collision with the Sagittarius dwarf elliptical galaxy, which started 7 billion years ago. And as I said earlier, this merger is not yet complete. So this is art by Roan Kelly. She's the artist at Astronomy magazine, and she made this art for my article about this topic in the August 2024 issue, and she kindly let me use it for tonight's presentation. So what Gaia found is that orbiting high above and below the plane of the Milky Way are the two Sagittarius star streams. These are not original Milky Way stars. They came from the Sagittarius dwarf elliptical galaxy, and they've been strewn out in rivers from the collision. And the Sagittarius dwarf elliptical galaxy is currently on the far side of the galaxy from us and plunging toward its fourth encounter with the Milky Way. But we can't really see it very well because the core of the galaxy blocks our view of it. But nonetheless, Gaia can spot where these stars are, and so have other astronomers, and they're contained in this elliptical distribution below the core of the Milky Way. And if you look at the very center of this remnant of the Sagittarius dwarf elliptical galaxy, there's a little dot. And that turns out to be the globular star cluster, quote unquote, M54 in Sagittarius, which is a very tightly clustered class 3 globular in the Shapley solar system. Now, it doesn't look like much. In fact, back in the 1990s, I wrote in my log for a Messier marathon, perhaps the most boring object in the Messier catalog. But it turns out this isn't a globular star cluster at all. Back in 1996, astronomers figured out that the chemical signatures of its stars do not match the Milky Way, but they match the Sagittarius dwarf elliptical galaxy. So this is the surviving core of the Sagittarius dwarf elliptical galaxy, and it's been masquerading as a globular star cluster for 2 centuries. But we now know it's the core of that galaxy that has collided with our own. So I no longer look at this galaxy with, or this globular cluster with disdain, because it turns out that the simulations show that when the Sagittarius dwarf had its first impact with the Milky Way galaxy, it triggered an enormous burst of star formation and spiral arm formation that included the spiral arm that contains our sun. So that collision with the dwarf elliptical galaxy is responsible for the formation of the sun, the Earth, and even us. All life on Earth, it wouldn't be here if that thing hadn't collided with us. So no, I don't look at this thing with disdain as perhaps the most boring object in the Messier catalog. Rather, I think it's an object to be sought out, observed, and even revered, because we owe our very existence to it. And so if you want to read more about these collisions, all of this is summed up in this article I wrote in the August 2024 issue of Astronomy. So to summarize, globular star clusters have tremendous astronomical and cosmological significance, and therefore are very worthy observing targets. They are great observing targets because they are beautiful, bright, large, and colorful. And I hope that you will become excited about globular star clusters and observe them often and share them with others, and look for some of the features that I described here that you may not have ever tried to pay attention to before. And remember, if anyone ever tries to say to you, the next time they tell you that if you've seen one globular star cluster, you've seen them all, based on this talk, I hope you can tell them otherwise. So thanks for your attention, and I'd be happy to take questions at this point about the talk.
Right. Thank you, Rod. And please, if you've got questions, feel free to unmute yourself and ask away.
I think there was one in the chat.
So Lee Race asked, I think this is a question, continuing your research, what do you expect to find next, or what do you hope to discover? Do you have an idea not yet proven?
So I think there are 2 fascinating directions that globular star clusters will move in. One is, do they have black holes at their centers like galaxies do? And thus far, we have found that their M13 that I showed has a black hole at its core, and so does NGC 6 something something something. Those are the only 2. It's not as easy as seeing the black holes at the center of galaxies because of the incredible densities of stars in the cores. And it's really hard to track the movements of the stars. But I think that, these things appear to be very hard to, when they plot the movements of these stars in the cluster around the core, it shows very tight movement, and that would be very hard to gravitationally disrupt them. Next is the blue stragglers. So it's like people ask, do globular star clusters have supernovas? And no, they don't, because supernovas come from young blue supergiant stars, and I told you they burn up their hydrogen in a few million years, and yet these clusters are billions of years old. So there are blue stars in globular star clusters, but they don't plot where blue giants were. They plot somewhere between the main sequence and the red giants, and that's why they're called blue stragglers, because it doesn't look like they're moving over to the red giant branch like they ought to. So the new discovery that has just come out this year is that they think that they come from collisions, that two smaller stars collide while they're buzzing in toward the center, and they, by adding their mass together, they form enough mass to make a blue giant star. And perhaps they will go supernova. I mean, no supernova has ever been witnessed in a globular star cluster in modern times. But if they merge and make a blue giant and then they burn out, maybe we'll see one.
Wow.
Hey, I got a question. So I'm assuming these globular clusters are like really stable because they've been around for like 13 billion years.
Yeah, and they survive
But is it possible?
galaxies.
Yeah, it's crazy. So, but is it possible for you said that sometimes they merge, stars merge together. Do you think with all the stars moving around that some stars could get slingshotted out of the globular?
Don't know. It could be that, and maybe what we're seeing is what's left after the unstable ones have been flung out. And if you ask what are globulars doing out there, the answer is not much. They move very slowly when they're way away from the plane of the Milky Way. Frank Drake calculated that, and he didn't have to worry about aiming ahead of M13. It's not going to move much in 25,000 years. He'll still hit it. But I think when they pass through the plane of the Milky Way, they probably lose a few stars, or maybe even they acquire some. We don't know.
Thank you, Rod. I've pulled up Rod's website, and I hope you're seeing it.
I'll stop sharing. I think
some of his pictures.
No, we can see it.
He's got some beautiful photographs, and of course, he's not limited to star clusters. He got some wonderful nebula pictures, galaxy pictures, and solar system stuff I haven't looked through yet. Supernovae. That's pretty cool. There's before and after. That right there.
Yep, you've spotted it.
Yeah. And this is his quite impressive observatory. Nice aluminum dome and telescope system set up. I was Steve mentioned a globular cluster story I have, which is I have been hooked on globular clusters since early in my astronomy hobby. I used to go down to French Camp Rainwater Observatory in French Camp, Mississippi. They have a bunch of people donated telescopes to this outreach school that's down there for wayward children, and they set up an observatory that's well, back then it wasn't nice equipment. The observatory wasn't much, but they've since vastly improved it. But all along, they've had this 30-inch Dobsonian, and I think maybe my second trip down there, they had the 30-inch out, and it wheels out of a building, and then you've got this 12, 13-foot tall, heavy-duty aluminum ladder you roll around to look at it. Or in late March, you just lay it down, point it due south, and stand on solid ground and look through an eyepiece that must have been this big around and look at Omega Centauri. Like you could just reach out and touch it. It was a wonderful three-dimensional view. Of course, it wasn't three-dimensional, but it just was absolutely gorgeous. You could count the stars in the center of it. You could see so deep into it. It was just mesmerizing. And I stood there for an hour looking at it, until it went out of the field of view, out of sight below the horizon again. So
It must have been
I've
pretty
been
low on
hooked
the
on them
horizon.
ever since. Of course, M13 is a favorite second, but I do love globular clusters. I do love staring at them, and I love peering into them. I love trying to resolve the stars toward the core. So I enjoy them. Thank you very much for your presentation tonight. I indeed learned stuff I did not know, and I'm intrigued by some of it. So I will be having to dig into some things to try to understand it better. Anyone else have any additional questions for our guests?
Well, Steve talked about getting him for our astrophotography group to talk about processing and doing more imaging of them. So we'll be in touch.
Okay, happy to do that. Turns out Omega Centauri is a core of a galaxy too, Rick.
Oh, really?
Yeah, I didn't talk about because I can't see it from here, so I don't have an image of it. So, but yeah, there's another galaxy that they.
You got one, Rick.
Oh, yeah.
Dude, let me.
It's the surviving core of that galaxy.
Let me share my desktop here.
Yeah, we want to see it. There it is.
Yeah, there it is.
Beautiful.
That's actually my desktop.
Yeah, Martin Pugh took that image. We bought it from him.
Process the data.
Oh, it's Martin's. Okay. How high was it above your horizon down there?
Oh, about that much.
2 degrees. It gets up to about 10 degrees.
I think, yeah, that's what I was
in Memphis.
10 degrees.
Yeah, but still, the fact that you had such an amazing view, even through 30 miles of air, tells us.
Absolutely. It was a particularly good night too. Steady seeing. So
That's good. Yeah.
it was just one of those. It was one of those times like when I used to sit I had a 10-inch Parkes Cassegrain.
Wow.
And I sat in my driveway and look at Jupiter with it was the F-13, and I had a 9 millimeter Nagler eyepiece in it, and I would just sit there and stare at Jupiter because just ever so often the bands would just snap into focus, and you go about the time you realize that they were gone again.
Yeah, but we'll wait forever for those moments, won't we?
Yeah, that's it. So
Somebody's got their picture, Adam, picture of the propeller. Good job.
I got a question about you. You showed us M22.
Mm-hmm.
Can you explain why there were so many blue stars there? Was it what you were just saying a minute ago that they borrowed gases from other stars and
No,
refilled?
we think. I mean, the new concept is. I mean, it's hard to explain how you could have blue giants in a globular cluster when they're that old. They
Right.
should have all burned out in supernovae long ago. But it's they're now coming up with very good evidence that these blue stragglers are from mergers of other smaller stars. They add their mass together, and then you get enough mass to have a blue giant. So, I'm not terribly familiar with the topology of Omega Centauri here. Those two blue stars in that image are probably foreground Milky Way stars, I would presume. But if you look at others, I mean, do you want me to go back to my M22 image?
Yeah, go ahead.
All right, we got to figure out share screen.
Well, Rick might be able to get to it.
Oh yeah, he could get to it on the website. You're gonna have to go to new images with the CDK 400, Rick. It should be down toward the bottom there somewhere. I think it's that globular right there that you went past, right above the Veil Nebula.
To the left.
Left.
There it is.
Sorry.
Yeah, a lot of blue stars there.
Yeah. And so those are all blue stragglers as far as we know. None of them are original blue supergiants. And you can see them in virtually all globulars. They're blue stars.
Mm-hmm.
Very nice.
And my final question to you, Rod, would be that you showed us M75. Would you, you're at star parties, and it's nice to throw fun facts out there.
Yeah.
Would you say that's like the furthest one we can see?
No, I didn't give you. I apologize. M54 is at a distance of 73,000 light years. So that, as far as I know, that's the farthest globular. But with the caveat, it's not a globular; it's the core of a galaxy.
Right.
But if you're gonna, it's like throwing Pluto out. We'd have to throw M70 or M54 and Omega Centauri out based on that.
Well, they're just downright pretty. That's all I got to say.
Fantastic presentation.
Thank you for inviting me.
Yes,
you guys are great bunch of guys. I want to join your society just to be a member.
It only costs $25.
Yeah, right.
And
so saith the treasurer.
And you see our treasurer there. He will collect it.
Okay, done. Agreed. Easy.
But I'll be in touch for a presentation later on this year.
Okay, great.
All right. Well, thank you very much, Rod. Thank you, everyone, for attending. We had a great attendance tonight, and appreciate you being a part of our society and enjoying what we do. So thank you very much. If that's everything, I will bid you all a good evening.